Hello everyone. In this video, we will begin to examine topic 1.2, uncertainties and errors. All right, so this is topic 1.2, uncertainty and error. This is one of the most important and longest lasting topics we will do. I will introduce sort of a set of concepts underlying uncertainty and error in this subsection that will be extremely important, particularly in conducting major lab practical work. So this is one of those sections that you want to attend to closely the first time and come back to as necessary. All right. When scientific measurements are taken, the measurements vary. So, for example, normally I would have you do this in class, but for the sake of the argument, consider every single student in the class being asked to drop a ball from the height of their desk and simply time how long it takes to hit the ground. So I hand out a variety of balls to different people. They all go to their desk. They take out their timers, and then they time many trials for the ball dropping from the top of the desk down to the floor. And what will happen is they will come up with a distribution that looks like this, perhaps with more X's. This is a histogram. So many students got something like 0.8 seconds, not very many got 0.7, and then a couple got 0.6. And whatever it happens to be, it will probably look a little bit like this. If we take a lot of data, it will look more and more like this bell curve, the normal distribution, for those of you who have seen that in stats class. And there'll be sort of a middle time right here, roughly in the center of whatever that bell curve fits for the x's, and there'll be times significantly above that and significantly below that. So everyone is, in theory, measuring the same thing. That is the time it takes for the ball to go from that height of the desk down to the floor. But these measurements vary, and that's our question here. So when scientific measurements are taken, the measurements vary. Why is that? Well, there are actually a couple of reasons, and often they're run together. So you want to be careful about the way you describe them and what we call them. The first reason is actually there is an intrinsic variation in the quantity being measured. All right, what does that mean? Well, imagine that if we were all in the classroom, the actual heights of the different desks that people were measuring turn out to be different, even though we thought they were the same, or perhaps we didn't think they were the same. But one of the reasons a measurement can vary is because the actual quantity being measured is varying. So for example, at any given moment, if I ask you to take the temperature outside, you'll all go outside, you'll use your thermometers, you'll come back in, and if you are all in different places, not to mention using different instruments, you will get different temperatures because the temperature varies from place to place and over time. Now, if you're all in the same place, taking the temperature at the same time in the same place, then for reasons having to do with sort of how temperature works, we expect the temperature to be the same. And so that would not be a source of variance. But if I asked everyone to take the temperature simply wherever they are, whenever they are, we will get variation in the quantity due to the fact that the actual thing being measured is changing. This is intrinsic variation, and it's important to distinguish it from either uncertainty or error, which we'll get to in a bit. This is addressed sometimes, not by being more precise, although you can do that as well. So, I could say instead of taking the temperature outside wherever you are, whenever you are, I can say take the temperature right now in Cheshire, Connecticut, right outside the physics classroom. That would be a way of sort of redefining the quantity to be very precise. There's a second way we deal with it, though, sometimes, is that we'll simply say, what we're interested is not the temperature, so to speak, but perhaps the average temperature, where we're explicitly acknowledging that intrinsic variation. So by saying that you want the average temperature, you know that the temperature is going to change. Let's say you want the average temperature over a single day. You know the temperature is going to change, but there is only one average temperature, and all of us should agree, if we're in the same place, on the total average temperature over the course of the day, even though there is still intrinsic variation in temperature. Why? Because there shouldn't be intrinsic variation in the average temperature, wherever you happen to be. So there are going to be a bunch of experiments we do where we have to be careful not to think of the intrinsic variation in what is being measured as itself error. It's not error, it's just the thing is changing or is different from time to time and from place to place. All right, well, as implied, the second major reason that measurements can vary is error, or sometimes we'll say errors in measurement, okay? And error is going to be a concept that we're going to look at a lot throughout this subunit, but it is formally defined as the deviation from the real or the true quantity. So error is something that only makes sense if you think there is a real value that you're trying to measure. So there is such a thing as the height of the table or the temperature outside right now. And if you make an error in measurement or you introduce error into your measurement, then what you record as the result of your measurement will be different from the real or the true quantity. And we use the word error formally to mean how far away it is from that real or true quantity. Errors can be of different sorts. They can be instrumental in nature, so they could be related to your measuring instrument. Your measuring instrument could introduce a deviation from the real or true quantity, even if you're using it perfectly. They could also be methodological. So you could have a very precise, perfect instrument, so to speak, but how you use it introduces some deviation from the real or the true quantity. That's methodological error. Now, consider a whole bunch of reasons that the time it took the ball to fall from the height of the desk to the floor might be different. Well, one we've already dealt with, which is perhaps the thing actually being measured is different. Perhaps the ball is different. Perhaps the height of the desk is different. But let's say those are all close enough to be identical. Why else might these times have varied so much? Well, as many of you are familiar with, reaction time is a totally reasonable answer to that question. It does take us a little while to sort of register that something has hit. That time, about 200 milliseconds, or in this case, 0.2 seconds, would sort of introduce error into our measurement. There might also be, however, and in fact almost always is, anticipation time. This is a word for what happens when you're using your stopwatch and you just hit it too early as the ball is falling. Why? Because you're sort of watching the ball fall. You're not really reacting to it hitting. Perhaps you are, if, for example, you have your back turned and you're listening to the sound of it hit. But more likely, you're watching it fall and sort of trying to time it with your finger. And often what will happen is that anticipation time will give you a shorter measurement than the real measurement should be. You might also have different results due to stopwatch precision. So different people might have different stopwatches that are more or less precise. The button on the stopwatch could be sticky, or the stopwatch could only measure to the nearest second, for example. Now, in practice, most of you have stopwatches that would be way, way, way more precise than is necessary. In other words, in this situation right here, as described, there's probably very little instrumental error in the timing, depending on what stopwatch you're using. We've discussed this one, and then the last two to sort of discuss briefly here would be, well, what happens if you're measuring the height of the desk and you discover that your ruler is too short, systematically too short. Someone as a practical joke, cut off a portion of your ruler. Well, at that point, no matter how many times you measure that height, you will register a height that is too low. So if you're measuring the height, there will be error in your measurement on the height because your ruler simply is not giving you the accurate value. That would be an instrumental error, or an error due to the instrument. Or perhaps the rulers are different heights. So we have sort of a variance going on. There are lots of other reasons that we can discuss in the future.